Hello, I'm Dr. Eric Gossett. I'm Professor Emeritus at Bethel University in St. Paul, Minnesota, USA. This is the extended version of a lecture that was presented at the 2022 World Mathematics Invitational Final Round Awards Ceremony. The topic of the lecture is to describe some very elaborate patterns that can be produced on the computer. And these patterns seem so complicated that you might wonder, how on earth can we draw these using a computer program? And the purpose of this lecture is to describe a fairly simple mechanism that allows us to produce these without an inordinate amount of work. What you're seeing now is a Java application I wrote to produce these Persian rugs. In a link below the link you use to watch this video, there should be information on how you can download that application, make sure you have a Java runtime system on your computer, and then run this program on your own computer. If you happen to see a rug pattern you really like, you can click on manual generation and then change these two parameters to produce the rug. The two parameters that totally determine each of these rugs are first a border color, which is a number between 0 and 15. So there are 16 different colors. And then a shift value, also a number from 0 to 15. The shift value's only purpose is to allow this program to produce a larger collection of rugs than would be possible without that. So the main thing to determine this are the color of the border and the shift value. If you click random generation, then every 10 seconds, the program will produce another rug. The inspiration for this rug generating application was a short article published in Mathematics magazine in 1997. This is a publication of the Mathematical Association of America. The article was written by Professor Ann M. Burns, who was at Long Island University at the time the article was written. The title of her article is Persian Recursion. You can find the article at this URL. You clearly would need to pause this video to copy that down. If you successfully arrive at that location, you'll find a small image of the cover of the magazine that had the article published. Notice that one of her Persian rugs is the cover photo. And you'll also have a copy of the first page of the article. If you are a subscriber to this magazine, then you can see a PDF file of the entire article. I'm going to address this lecture by answering 4 questions. The first question is, what are the main ideas for creating Persian rug patterns on a computer? I'm going to look at the intuitive ideas behind how to use the computer to do this, and we'll do that on graph paper so that you can follow along. The second question is, which values of n can be used for the size of the n by n grid that the rug is colored onto? Not every value of n will work. Question 3 addresses how we can program a computer to draw the rugs. And that will involve looking at some high-level descriptions of the program called pseudocode. You don't need to know any computer languages to follow this part. The final question is, how can we get the computer to randomly change colors in a manner that builds symmetry into the patterns? So, what are the main ideas for creating Persian rug patterns on a computer? At this point, you may want to pause the video and get some graph paper and 6 colored pencils of different colors. Rather than using graph paper, I'm going to actually use a website called virtualgraphpaper.com. And to do that, I want to show you a little bit about how to use this program if you choose. When you first start, you want to go to Setup, and the subdivision 4 is why we have 4 smaller rows and columns inside of these bigger squares. I want to change that to 1 so that our squares look like single pixels. Secondly, you want to click on the word rectangle. We're going to be filling in rectangles. Notice up in the top left corner, there are some little hints to drawing. The way the algorithm works is it first fills in the border color. Here I'm filling in a border of a 9 by 9 grid. I happen to choose the color blue. Then the program starts repeating the following process. It looks at the 4 corners of the colored border, the 4 corners around the currently uncolored region, and it determines what those colors are. In this case, we have 4 blue. And the program will then choose to pick a color. I'll use green, so that anytime it finds an uncolored region with 4 blue corner squares, it will color a new color of green by filling in a plus sign in the middle. In this program, using the rectangle tool, I can grab the upper left corner of what I want, drag down, and then click again to make that stick. So I want to draw the rest of the plus sign. Notice that this plus sign has divided the uncolored region into 4 smaller uncolored sections. To change colors, notice I have to click on the color here, the stroke, pick a color, and then click somewhere else to close the color palette, and I have to do the same thing with the fill. Now, what the algorithm will then do is it will determine to color this 3 by 3 uncolored region, and it does that by looking at this sub-region of the rug. It has a border. On the border, there are 3 blue squares and 1 green square. It knows to use green whenever there are 4 blue colors on the corners. It needs to make up a new color now whenever there are 3 blue and 1 green. I think I'll use red as my next, so I click to open the palette, click on a color, click again to close the palette. And so up here with 3 blue and 1 green, I'm going to color in a red plus. Now the way the algorithm will work, it will try and color this square next, but for doing it on graph paper by hand, it's probably easier if we work on all 4 of these squares in parallel. And so I'm going to color this plus sign in red because there are 1, 2, 3 blue and 1 green corners for this square as well. And that happens to be true for the lower right and the lower left. At this point, the algorithm is going to then determine what to do with the smaller section. It's up in this top corner, and it has this smaller section here to worry about. And what we notice is that the corners on the uncolored square happen to be 3 blue and 1 red. Previously, we've had 4 blue producing green. We've had 3 blue and a green producing red, but here we have 3 blue and a red. That's a different combination, so I need a new color. I think I'll pick pink this time. And so we can color this in as pink. Now notice that this square also has 3 blue and 1 red, so I should color it pink as well as these 2. But what we should notice next is that none of the other squares have borders that have the same combinations. This next uncolored square has 2 blue, 1 red, and a green. That's a new combination, so we need a new color. Maybe I'll pick yellow for that. I color this in with yellow. Notice that this uncolored square also has 2 blue, a green, and a red, as do the following squares that I'm coloring yellow. All of those have the same color. And so to preserve the symmetry, we fill those in the same. Well, what about the remaining squares? What we notice here is that we have 3 green and 1 red. That again is a new combination. And so we again need a different color. Maybe I'll pick orange. This also has 3 green and 1 red. So we'll color all of the ones with 3 green and 1 red with orange. And that completes the Persian rug. So to review, we color the first color around the border. And then after that, we look at the corners around the uncolored region and use those corners to choose a new color and paint a plus sign. And we keep painting plus signs until we get to the point where we can't do a plus sign. We just have a single square left, and then we just color that square with the new color. The second question is which values of n can be used for the size of the n by n grid that we're coloring. In the example, I used a 9 by 9 grid of cells or pixels. Why did I choose that? Well, think about what happens after I color in that first green plus sign. Before the green plus sign, there are 7 columns and 7 rows of uncolored squares. Once I color the plus sign, I have only 6 columns, and I want to divide those into 2 equal groups of size 3. Similarly, once I do the horizontal line, I have 6 remaining uncolored rows of which I want to divide into 2 equal groups. In this notion of continuing to divide into 2 equal groups over and over suggests that the size that we want to start with for the grid should be divisible by 2 many times. That is, we want our number related to 2 to the k for some integer. But we do the division only after we color in a plus sign. And so that uses up 1 cell in each row and in each column. So instead of starting with an even number of cells, we want to start with an odd number, which we can express as 2 to the k minus 1. But we also needed some cells for the border. The border cells use up 2 cells for each row and 2 cells in each column. So we need to add 2 to this number to have 2 to the k plus 1 rows, 2 to the k plus 1 columns. Notice that 9 is 2 to the 3. 2 to the 3 is 8, plus 1 is 9, and that's why I chose 9. Also, it's a nice example that's not too large to do by hand, but large enough to show the process. The Java application I showed at the beginning of the lecture uses a 513 by 513 grid. 2 to the 9th is 512, adding 1, I get 513. If you're interested in doing more by hand, you might try using a 17 by 17 grid. 17 is 2 to the 4th plus 1, and so that's the next size bigger than 9 by 9 that we can use and have this algorithm work. Question 3, how can we program a computer to draw the rugs? The computer runs a program that uses 4 copies of itself to color smaller portions of the rug. Just as we know, the plus sign divides the region into 4 smaller regions, this program is going to use itself to color those smaller regions. And so this technique of using its own code to solve a smaller problem is called recursion. I'm going to use a high-level description called pseudocode to describe this recursive code that colors a Persian rug. And it does assume that there are 2 to the k plus 1 rows, 2 to the k plus 1 columns. The code consists of 2 programs, a main program color rug and a helper program color square. Color rug takes a single parameter, which is the color to put around the border. We used blue. It does two things. It colors the border using the border color, and then it calls the helper function by passing in the entire rug and a new color, which we'll have to someday worry about how it comes up with a new color. But for now, just assume that it makes up a new color and sends it in. Color square takes the region it needs to color the whole thing initially and the new color, and it does the following. It first checks if the color region the region that's just been passed has more than 4 pixels. Originally on our graph, we had a 9x9 grid, which has 81 pixels, so that certainly is true. If this ever gets a 4x4 region, that will be a region where the 4 pixels rather, not 4x4, 1x1, the 2x2, the 4 pixels will be already the border with nothing left to color on the inside. If there's nothing left to color on the inside, we want to go down and do nothing. So assuming that there are more than 4 pixels, we're going to calculate a new color or find a new color in some magical way and color in the plus sign. At that point, we have 4 smaller subregions, and color square will call its own code, passing in the 4 different smaller subregions and an additional new color that it picks. So notice that this helper function, color square, actually calls itself 4 times, each on a smaller portion of the grid. And that's the part that is instituting the recursion. Fortunately, all modern programming languages support recursion. So if you know a language, you should be able to do recursion. Also, again, let me emphasize that the first thing this recursive function does is check to see if it's done. If we don't stop when there's nothing left to color, these will each keep calling newer regions that are too small to color but don't know to stop, and the program will run forever. Finally, how can we get the computer to randomly change colors in a manner that builds symmetry into the patterns? And the key idea is to use this notion we developed when we colored the graph. We're going to use some simple but clever arithmetic to implement the idea that plus sign colors should be determined by the colors of the 4 corner squares. To do that, we need to do arithmetic, and so we're going to convert from colors into integers. So the next version of the code, the recursive code, is going to create and calculate a new color at each step, thus preserving the symmetry. And to do that, I'm going to assign integers to represent colors. So I've chosen to use 16 different colors, and I'm going to number those colors from 0 to 15. So for example, the number 6 might represent the color blue. Here's the new code. Color rug now has 2 parameters, the border color, which is an integer between 0 and 15, and the shift number, also from 0 to 15. The shift, again, is just there to make sure that the program can generate lots and lots of different rugs. Color rug colors the border using the border color number, and then it calls color square, passing it the rug and this shift value, which remains unchanged throughout the entire generation of the rug. Color square checks to see if there are at least more than 4 pixels. If not, it does nothing. If there are at least 4 pixels, it's going to calculate a new color in a way we'll look at in a minute. It uses that new color to paint the plus sign, and then it calls itself on each of the 4 uncolored subregions, passing in that same unchanged shift value. The new color function is calculated by taking the 4 integers in the border corner squares, which represent the colors, the top left, top right, bottom left, bottom right number, adding those, dividing by 4. This is an integer arithmetic, and so we're interested in the quotient. If there's any remainder, we just throw it away. We add that integer to the shift value, and then we look for the remainder when we divide by 16. So notice that the new color is completely determined by the integers of the colors surrounding the 4 colors of the border of this new subregion. Nothing else changes the color. The shift value never changes throughout the entire process. The fact that the 4 border corner colors determine the new color guarantees that we will have a symmetry to our design. Now, how does this mod function work? Mod 16. N mod k means divide the integer n by k and keep the remainder. So for example, 19 mod 16 is 3. Why is that? 16 goes into 19 one time with a remainder 3, and the remainder is what we're interested in. 16 mod 16 is 0. Why is that? 16 goes into 16 one time with a remainder of 0. The last example, 4 mod 16 is 4. 16 goes into 4 0 times with a remainder of 4. The remainder mod 16 is there to guarantee that the answer is always a number between and including 0 to 15. This ensures that the new color will always be one of the 16 colors that I have chosen to use. Here's an extended example then to illustrate this new pseudocode. Let's assume that the initial color is 6 and the shift constant is 12 for this rug. So color rug colors in the border color 6, and then it calls color square by passing this entire rug in and the number 12. At line 7, it checks that there are more than 4 pixels. There's actually 81 pixels, so that's okay. It calculates a new color by looking at the 4 border colors, which all happen to be 6. 24 divided by 4 is 6. Add that to the 12, we get 18. 18 mod 16 is 2. And so we color in line 9 a plus sign out of the color 2. Then at line 10, it wants to pass in the subregion bordered by these cells, or easier to see, it passes in this subregion to color square at line 10, and color square starts all over with that sub piece. First thing it does is check that there are more than 4 pixels. There's 25, so that works. And so it's ready to calculate a new color. It uses the 4 border colors, 6, 6, 6, and 2. That adds up to 20. When we divide by 4, we get 5. Add that to 12 is 17. 17 mod 16 is 1. And so we fill in the color 1 in line 9. And now we're going to pass in at line 11 this subregion. This subregion has border colors 6, 6, 6, and 1. We add those and get 19 and divide by 4. Remember that 4 goes into 19 4 times with remainder 3, but we only keep the quotient. We throw the remainder away. 4 plus 12 is 16. 16 mod 16 is 0. And so the color in that empty spot should be 0. We can then fill in the remaining 3 empty squares in this top region. For instance, these 2 15s come from blank squares before they're colored with 6, 6, 2, and 1. So we add those and get 15. 4 goes into 15 3 times. Throw the remainder away. Add that to 12 is 15. 15 mod 16 is 15. And so those 2 squares get color 15. This one gets color 13 because its border colors are 2, 2, 2, and 1. So we get 7/4, which has a quotient of 1. Add to get 13. 13 mod 16 is 13. So once that initial recursion of this top left corner is done, it'll pass in the top right corner, then the bottom left corner, the bottom right corner, and you can verify that we'll get a rug that looks something like this, depending on how we assign colors to the numbers. So using a couple of simple mathematical ideas, namely powers of 2. In this case, we start with a rug that has 2 to the k plus 1 rows and columns. And then using integer division and the mod function, and one new idea from computer programming, namely recursion, it's not too difficult to produce very elaborate Persian rug patterns. Well, thank you for watching this video. I hope you continue to enjoy doing math and participating in the World Mathematics Invitationals in the future.